Hello, guys, welcome to a new chapter of the future of humanity. This is going to be chapter 9, Kepler and a universe of planets. Every few days, Giordano Bruno has his revenge. Bruno, Galileo's predecessor, was burned alive at the stake for heresy in Rome in 1600. The stars in the heavens are so numerous, he observed, that our sun must be one of many. Surely these other stars, too, are orbited by a multitude of planets, some of which may be even inhabited by other beings. The church imprisoned him for 7 years without trial, then stripped him naked, paraded him through the streets of Rome, tied his tongue with a leather strap, and lashed him to a wooden pillar. He was given one last chance to recant, but he refused to take back his ideas. To squelch his legacy, the church placed all of his texts on the index of forbidden books. Unlike Galileo's works, Bruno's were banned until 1966. Galileo merely claimed that the sun, not the earth, was the center of the universe. Bruno suggested that the universe had no center at all. He was one of the first in history to posit that the universe might be infinite, in which case the earth would be just another pebble in the sky. The church could no longer claim to be the center of the universe because it had none. In 1584, Bruno summed up his philosophy, writing, "This space we declare to be infinite. In it are an infinity of worlds of the same kind as our own." Now, more than 400 years later, roughly 4,000 extrasolar planets in the Milky Way have been documented, and the list grows almost daily. In 2017, NASA listed 4,496 candidate planets, of which 2,330 have been confirmed, discovered by the Kepler spacecraft. If you go to Rome, you might want to visit the Campo de' Fiori, the Plain of Flowers, where there is an imposing statue of Bruno on the very spot where he faced his death. When I went, I found a bustling square full of shoppers who may not at all be aware that the location had been an execution site for heretics. But Bruno's statue, it gazes down upon a number of young rebels, artists and street musicians who unsurprisingly congregate there. While taking in this peaceful scene, I wonder what kind of atmosphere could have existed back in Bruno's day to inflame such a murderous mob. How could they be whipped up to torture and kill a vagabond philosopher? Bruno's ideas languished for centuries because finding an extrasolar planet is exceedingly difficult and was once thought to be nearly impossible. Planets do not give off light on their own. Even the reflected light of one is about 1 billion times dimmer than that of the mother star, the harsh glare of which can obscure the planet from view. But thanks to the giant telescopes and space-based detectors, we have today a flood of recent data that has proven Bruno to be correct. In my childhood, I read an astronomy book that changed the way I understood the universe. After describing the planets, the book concluded that our solar system was probably a typical one, echoing the ideas of Bruno. But it also went much further. It speculated that planets in other solar systems moved in almost perfect circles around their sun, like ours. The ones closer to the sun were rocky, while the ones farther out were gas giants. Our sun was the average Joe of stars. The notion that we live in a quiet, ordinary suburb of the galaxy was simple and comforting, but boy were we wrong. We now realize that we are the oddballs and that the arrangement of our solar system, with its orderly sequence of planets and near-circular orbits, is rare in the Milky Way. As we begin to explore other stars, we are coming across solar systems cataloged in the Extrasolar Planets Encyclopedia that are radically different from our own. One day this encyclopedia of planets may contain our future home. Sarah Sager, professor of planetary science at MIT and one of Times Magazine's 25 most influential figures in space exploration, is a key astronomer behind this encyclopedia. I asked her whether she was interested in science as a child. She admitted to me that actually she was not, but the moon did catch her attention. She was intrigued by the fact that it seemed to follow her whenever her father drove her around. How could something so far away appear to chase after the car? The illusion is caused by parallax. We judge distances by moving our heads. Close objects like trees seem to shift the most, while distant entities like the mountains do not change position at all. But objects immediately next to us that are moving with us also don't appear to change position. Our brains therefore confuse remote objects like the moon with adjacent ones, like the steering wheel in the car, and make us think that both are moving consistently alongside us. As a result of parallax, many of the UFOs spotted trailing after our cars are actually sightings of the planet Venus. Professor Sager's fascination with the heavens blossomed into a lifelong romance. Parents sometimes buy telescopes for their inquisitive children, but she bought her own first telescope with the money she earned from a summer job. She remembers being 15 and excitedly talking to two of her friends about an exploding star named Supernova 1987A that had just been seen in the sky. It had made history as the closest supernova since 1604, and she was planning to go to a party to celebrate the rare event. Her friends, however, were baffled. They did not know what she was talking about. Professor Sager went on to convert her enthusiasm and sense of wonder about the universe into a bright career in exoplanet science, a discipline that didn't exist 2 decades ago, but that is now one of the hottest fields in astronomy. It is not easy to see exoplanets directly, so astronomers find them with a variety of indirect strategies. Professor Sager stressed to me that astronomers are confident of the results because they detect exoplanets in multiple ways. One of the most popular is called the transit method. Sometimes when analyzing the intensity of a starlight, you notice that it weakens periodically. This dimming is a small effect, but indicates the presence of a planet from the vantage point of Earth has moved in front of the mother star, thereby absorbing some of the light. Since the path of the planet can therefore be tracked, its orbital parameters can be calculated. A Jupiter-sized planet would reduce light from a star like our Sun by about 1%. For a Earth-like planet, the figure is 0.008%. This is like the dimming of a car's headlight if a mosquito passes in front of it. Fortunately, as Professor Sager explained, our instruments are so sensitive and accurate that they can pick up on the slightest change in luminosity from multiple planets and prove the existence of entire solar systems. However, not all exoplanets move in front of a star. Some have tilted orbits and therefore cannot be observed by the transit method. Another popular approach is the radial velocity or Doppler method, in which astronomers look for a star that seems to move back and forth regularly. If there is a large Jupiter-sized planet orbiting the star, then the star and its Jupiter are actually orbiting each other. Think of a rotating dumbbell. The two weights representing the mother star and its Jupiter turn around a common center. The Jupiter-sized planet is invisible from a distance, but the mother star can clearly be seen moving in a mathematically precise fashion. The Doppler method can be used to calculate this velocity. Careful examination of the mother star over weeks and months also enables scientists to estimate the mass of the planet using Newton's laws of gravity. The Doppler method is tedious, but it led to the discovery of the first exoplanet in 1992, which set off a stampede of ambitious astronomers trying to track down the next exoplanets. We have the direct observation, which, as previously mentioned, is difficult to accomplish. However, Professor Sager is excited by NASA's plans to develop space probes that can carefully and precisely obstruct the light from the mother star, which might otherwise overwhelm the planet. Gravitational lensing may be a promising alternate method, although it only works if there is perfect alignment between the Earth exoplanet and the mother star. We know from Einstein's theory of gravity that light can bend as it moves near a celestial body, because a large mass can alter the fabric of space-time around it. Even if the object is not visible to us, it will change the trajectory of light just as clear glass does. If a planet moves directly in front of a distant star, the light will be distorted into a ring. This particular pattern is called an Einstein ring and signals the presence of a substantial mass between the observer and the star. A big breakthrough came with the 2009 launch of the Kepler spacecraft, which was specifically designed to find extrasolar planets by employing the transit method. It was successful beyond the wildest dreams of the astronomical community. Next to the Hubble Space Telescope, the Kepler spacecraft is probably the most productive space satellite of all time. It is a marvel of engineering, weighing 2,300 pounds with a massive 4.6-foot mirror and bristling with the latest high-tech sensors. Because it has to stare at the same spot in the sky for long periods of time in order to get the best data, it does not orbit the Earth, but circles the Sun instead. From its perch, in deep space, which can be 100 million miles from Earth. It uses a series of gyroscopes to focus on 1/400th of the sky, a small patch in the direction of the constellation Cygnus, inside that tiny field of vision. Kepler has analyzed about 200,000 stars and uncovered thousands of extrasolar planets. It has forced scientists to reevaluate our position in the universe. Instead of locating other solar systems resembling our own, astronomers came across something totally unexpected: planets of all sizes orbiting stars at all times. There are planets out there that have no counterpart in the solar system, some of which are in between the size of the Earth and Neptune or much smaller than Mercury. Professor Sager reflected, but today we still haven't found any copies of our solar system. In fact, we still haven't found any copies of something similar. The more we find, the less we understand, she confessed. The whole thing is a mess. We are at a loss to explain even the most common of these exoplanets. Many of the Jupiter-sized planets, which have been the easiest to find, are not moving in near circular trajectories as expected, but in highly elliptical orbits. Some Jupiter-sized planets are in circular orbits, but they are so close to the mother star that if they were put in our solar system, they will be within the orbit of Mercury. These gas giants are called hot Jupiters, and the solar wind is constantly blowing their atmosphere into outer space, but astronomers once believed that Jupiter-sized planets originate in deep space, billions of miles from the mother star. If so, how did they get so close? Professor Sager admits that astronomers don't know for sure, but the most probable answer took them by surprise. One theory states that all gas giants form in the outer regions of a solar system where there is plenty of ice around which hydrogen and helium gas and dust can collect, but in some cases there is also a large amount of dust spread out within the plane of the solar system. The gas giant may gradually lose energy from the friction of moving through the dust, entering into a death spiral towards the mother star. This explanation introduced the heretical idea of migrating planets, which had been previously unheard of. In hindsight, this strange result should have been anticipated. Because our own solar system has planets moving in nice circles, astronomers naturally assume that the balls of dust and hydrogen and helium gas that become solar systems condensed evenly. We now realize that it is more likely that gravity compresses them in a haphazard, random way, resulting in planets that move in elliptical or irregular orbits that may intersect or collide with one another. This is important because it may be that only solar systems with circular planetary orbits like ours may contain life. Earth-like planets are small and hence cause faint dimming or subtle distortions of light from the mother sun, but with the Kepler spacecraft and gas and giant telescopes, astronomers have begun to locate super-Earths, which, like Earth, are rocky and capable of sustaining life as we know it, but are 50% to 100% larger than our planet. We cannot yet account for their origin, but in 2016 and 2017, a series of sensational headline-grabbing discoveries about them were made. Proxima Centauri is the closest star after our Sun to the Earth. It is actually part of a triple star system and orbits a pair of larger stars called Alpha Centauri A and B, which orbit each other. Astronomers were stunned to come across a planet just 30% larger than the Earth moving around Proxima Centauri. They name it Proxima Centauri b. This is a game changer in exoplanetary science, declared Rory Barnes, an astronomer at the University of Washington in Seattle. The fact that it's so close means that we have the opportunity to follow up on it better than any other planet discovered so far. The next batch of giant telescopes are in development. Like the James Webb Space Telescope, they might be able to capture the first photograph of the planet. As Professor Sager put it, it's absolutely phenomenal. Who would have thought that after all these years of wondering about planets, that there is one around or near a star? Proxima Centauri's B's mother star is a dim red dwarf only 12% as massive as our Sun, so the planet must be relatively close to the star in order to be inside its habitable zone, where it can support liquid water and possibly even oceans. The radius of the planet's orbits is just about 5% of the radius of the Earth's orbits around the Sun. It also revolves around its mother star much faster, making one complete revolution every 11.2 days. There is intense speculation information about whether Proxima b has conditions compatible with life as we know it. One major concern is that the planet might be bombarded by solar winds, which could be 2,000 times more intense than those hitting the Earth. To shield itself against these blasts, Proxima Centauri b will have to have a strong magnetic field. At present, we do not have enough information to determine whether this is the case. It has also been suggested that Proxima Centauri b may be tidally locked, so that, like our moon, one side always faces the star. That side will be perpetually hot, while the other side will be permanently cold. Liquid water oceans might then occur only at the narrow band between these two hemispheres, where the temperature is moderate. However, if the planet has a dense enough atmosphere, the winds might equalize the temperature so that liquid oceans could exit freely across its surface. The next step is to determine the composition of the atmosphere and whether it contains water or oxygen. Proxima Centauri b was detected using the Doppler method, but the chemical composition of its atmosphere is best assessed with the transit method. When an exoplanet crosses directly in front of the mother star, a tiny sliver of light passes through its atmosphere. Molecules of certain substances in the atmosphere absorb specific wavelengths of starlight, allowing scientists to determine the nature of those molecules. However, for this to work, the orientation of the exoplanet's path must be just right, and there is only a 1.5% chance that Proxima Centauri's b orbit is aligned correctly. It will be an astonishing coup to find molecules of water vapor on an Earth-like planet. Professor Sager explained that if you have a small rocky planet, you can only have water vapor if you also have liquid water on its surface. So if we find water vapor on a rocky planet, we can indeed find liquid oceans. Another unprecedented finding came in 2017. Astronomers located a solar system that violated all the theories of planetary evolution. It contains 7 Earth-sized planets orbiting a mother star called TRAPPIST-1. 3 of the planets are in the Goldilocks zone and may have oceans. This is an amazing planetary system, not only because we have found so many planets, but because they are all similar in size to the Earth. And Michael Guillon, the leader of the Belgian scientific group that made the discovery, said so. TRAPPIST-1 is a red dwarf, a mere 38 light years from Earth, and the mass is about 8% of that of the Sun. Like Proxima Centauri, it has a habitable zone. If transported over our own solar system, the orbits of all 7 planets will fit inside Mercury's path. The planets take less than 3 weeks to circle their mother star, and the innermost makes a complete revolution at 36 hours. Because the solar system is so compact, the planets interact gravitationally and could, in theory, disrupt their own arrangement and collide. One might naively expect them to carry into each other, but fortunately, as an analysis in 2017 showed that they are in resonance, meaning that their orbits are in phase with one another and no collisions will take place. The solar system seems to be stable. But as with Proxima Centauri b, astronomers are investigating the possible effects of solar flares and tidal locking. On Star Trek, whenever the Enterprise is about to encounter an Earth-like planet, Spock announces that they are approaching a Class M planet. Actually, there is no such thing in astronomy yet. Now that 1,000 of different planets have made their debut, including a variety of Earth-like planets, it's only a matter of time before a new nomenclature is introduced. If a planetary twin of the Earth exists in space, it has eluded us so far, but we have found about 50 super-Earths so far. Kepler 452b, which was discovered by the Kepler spacecraft in 2015 and is about 1,400 light years away from us, is particularly interesting. It is about 50% bigger than our planet, so you will wait more than you do now on the planet Earth. But otherwise, living there may not be so different from living on Earth, unlike the exoplanets that orbit around a red dwarf. It circles a star that is only 3.7% more massive than the Sun. Its period of revolution is 385 Earth days, and its equilibrium temperature is 17 degrees Fahrenheit, slightly warmer than the Earth. It lies within the habitable zone. Astronomers searching for extraterrestrial intelligence train their radio telescopes to receive messages from any civilization that might be on the planet, but have detected nothing. Unfortunately, because Kepler 452b is so far away, even the next generation of telescopes will not be able to collect significant information about its atmospheric composition. Kepler 22b, which is 600 light years away and is 2.54 times the size of the Earth, is also being studied. Its orbit is 15% smaller than the Earth's. It completes one revolution in 290 days, but the luminosity of its mother star, Kepler 22, is 25% lower than the Sun. These two effects compensate for each other, so the surface temperature of the planet is believed to be comparable to that of the Earth. It also lies in the habitable zone, but KOI 7711 is the exoplanet that is getting the most attention, because, as of 2017, it is one with the most Earth-like features. It is 30% larger than Earth, and its mother star is very much like our own. It is not at risk of being fried by solar flares. The length of 1 year on the planet is almost identical to a year on the Earth. It is in the habitable zone of its star, but we do not yet have the technology to evaluate whether its atmosphere contains water vapor. All conditions seem right for it to host some form of life. However, at 1700 light years away, it is the farthest exoplanet of the three. After analyzing scores of these planets, astronomers have discovered that they can usually be arranged into two categories. The first is the super-Earths, like those in the image, but we have been discussing mini Neptunes in the other. They are gaseous planets about 2 to 4 times the size of the Earth and do not resemble anything to our immediate vicinity. Our Neptune is 4 times bigger than Earth. Once a small planet is discovered, astronomers try to determine which category it belongs to. This is like biologists trying to classify a new animal as either being a mammal or a reptile. One mystery is why these categories aren't represented in our own solar system when they seem to be so prominent elsewhere in space. Rogue planets are among the strangest celestial bodies that have been discovered so far. They wander the galaxy without orbiting any particular star. They probably wander the galaxy without orbiting anything specific and originate in solar systems, but got to either too close to Jupiter-sized exoplanets and were probably hurled into deep space. As we have seen, these large Jupiter-sized planets frequently have elliptical orbits or migrate in a spiral towards the mother star. It is likely that their paths intersected with the smaller planets, and as a consequence, rogue planets might be more plentiful than ordinary ones. In fact, according to some computer models, our own solar system may have ejected 10 or so rogue planets billions of years ago. Because rogue planets are not near a light source and give off no light themselves, it seemed hopeless at first to try to locate them, but astronomers have been able to find, through the gravitational lensing technique, which requires a very precise and quite rare alignment to take place between the background star and the rogue planet and the detector in Earth. As a result, one has to scan millions of stars in order to detect a handful of rogues. Fortunately, this process can be automated so that computers and not astronomers do the searching. Thus far, 20 potential rogue planets have been identified, one of which is only 7 light years away from Earth. However, another recent study conducted by Japanese astronomers who examined 50 million stars found even more possible candidates, up to 470 rogue planets. They estimated that there might be 2 rogue planets for every star in the Milky Way. Other astronomers have speculated that the number of rogue planets could exceed the number of ordinary ones by a factor of 100,000. Can life as we know it exist on our own rogue planets? It depends. Like Jupiter or Saturn, some may have large numbers of ice-covered moons. If so, tidal forces could melt the ice into oceans where life may originate. But in addition to sunlight and tidal forces, there is a third way in which a rogue planet may have an energy source that could give birth to life: radioactivity. An episode from the history of science might help to illustrate this point. In the late 19th century, a simple calculation done by the physicist Lord Kelvin showed that Earth should have cooled down a few million years after its creation and therefore should be frozen solid and inhospitable to life. This result sparked a debate with biologists and geologists who insisted that the Earth was billions of years old. The physicists were shown to be wrong when Madame Curie and others discovered radioactivity. It is the nuclear force at the core of the Earth, from long-lived radioactive elements like uranium, that has kept Earth's core hot for billions of years. Astronomers have conjectured that rogue planets too might have radioactive cores that keep them relatively warm. This means that radioactive core could supply heat to hot springs and volcanic vents on the bottom of an ocean where the chemicals of life may be created. So if rogue planets are as numerous as some astronomers believe, then the most probable place to find life in the galaxy may not be within the habitable zone of a star, but on the rogue planets and their moons. Astronomers are also researching a plethora of completely star-twinned planets, some of which defy categorization. In the movie Star Wars, the planet Tatooine revolves around two stars. Some scientists scoffed at this idea, because such a planet would be in an unstable orbit and would collapse into one of the stars, but planets circling three stars have been documented, as in Centauri's system. We have even found 4 star systems in which 2 sets of double stars move around each other. Another planet has been discovered that apparently may be made of diamonds. It is called 55 Cancri E and is about double the size of the Earth, but weighs about 8 times more. In 2016, the Hubble Space Telescope successfully analyzed its atmosphere, the first time this has ever done with a rocky exoplanet. It detected hydrogen and helium, but no water vapor. Later, the planet was found to be rich in carbon, which might constitute about a third of its mass. It is also scalding hot, with a temperature of 5,400 degrees Kelvin. One theory postulates that the heat and pressure in the core may be extraordinary enough to give rise to the diamond planet. However, these glittering deposits, if they indeed exist, are 40 light years away from us, so mining them is beyond our current capabilities. Possible water wars and ice wars have also been located. This is not necessarily unanticipated. It is believed that our own planet, early in its history, was covered in ice, a snowball Earth. At other times, when the ice age receded, the planet was flooded with water. Gliss 1214b, the first of 6 known potentially water-covered exoplanets to be identified, was found in 2009. It is 42 light years away and 6 times larger than the Earth. It lies outside the habitable zone, orbiting 70 times closer to its mother sun than the Earth does. It may get as hot as 280 degrees Celsius, so life as we know it probably cannot exist. Both by using various filters to analyze large light scattered through the planet's atmosphere as it transits the mother star, significant amounts of water have been confirmed. The water may not be a familiar liquid form due to the planet's temperature and pressure. Instead, Gliss 1214 might be a steam planet. We have to come to striking realization about the stars. We once thought that our yellow star was typical in the universe, but astronomers now believe that dim red dwarf stars, which emit only a fraction of the light of our sun and usually cannot be seen with the naked eye, are the most common. By one estimate, 85% of the stars in the Milky Way are red dwarfs. The smaller a star is, the slower it burns hydrogen fuel and the longer it can shine. Red dwarfs may last for trillions of years, far longer than the 10 billion year lifespan of our sun. Perhaps it is not surprising that Proxima Centauri and the TRAPPIST system both involve red dwarfs, because they are so numerous. The Kepler spacecraft has surveyed enough planets in the Milky Way galaxy that a rough census can be made. The data indicated that on average every star you see has some kind of planet orbiting around it. About 20% of the stars like our sun have Earth-like planets, that is, are similar to the Earth in size and are in a habitable zone. Since there are roughly 100 billion stars in the Milky Way, about 20 billion Earth-like planets may exist in our backyard. It is this fact, which is a conservative estimate, that the actual number can be even higher. Unfortunately, the Kepler spacecraft, after sending a mountain of information that changed the way we conceptualize the universe, began to malfunction. One of its gyroscopes started to fail in 2013 and it lost the ability to lock into planets. But further missions are being planned that will continue to augment our understanding of the exoplanets. In 2018, the Transiting Exoplanet Survey satellite TESS will be launched. Unlike the Kepler, it will scan the entire sky. TESS will be examining 200,000 stars over a 2-year period, concentrating on stars that are 30 to 100 times brighter than those inspected by Kepler, including all the possible Earth-sized planets on super-Earths in our region of the galaxy. A number of astronomers expect it to be around 500. Furthermore, the James Webb Space Telescope, the replacement for the Hubble, will be inaugurated shortly and should be able to actually photograph some of these exoplanets. Earth-like planets may be prime targets for future starships. Now that we are on the cusp of investigating them in depth, it is important to explore two considerations: living in outer space with the biological demands that it will entail, and encountering life in space. We must first take a look at our existences on the Earth and how it may be enhanced to meet these new challenges. We may have to modify ourselves, extending our lifespan, adjusting our physiology, and even altering our genetic heritage. We will also have to contend with the possibility of discovering anything from microbes to advanced civilizations on these planets. Who might be out there, and what would it mean for us to meet them?